Welcome to lecture 30. So, this is the last week of week 6, and in this week 6 we are talking about direct search methods for unconstrained multivariable functions. In last few lectures we have talked about two methods for unconstrained multivariable functions which are classified as direct search methods, namely simplex methods and Hook-and-Jeeves method, Hook-and-Jeeves pattern search method. So, today we will talk about another direct search method known as Powell's conjugate direction method. Powell's conjugate direction method is an extension of the basic pattern search method that we have seen in our last lectures. It is one of the most successful and widely used direct search method. Powell method is a method of conjugate directions. A conjugate directions method will minimize a quadratic function in a finite number of steps. So, that is a nice property of methods based on conjugate directions. The conjugate directions method can minimize a quadratic function in a finite number of steps. A general nonlinear function can be approximated reasonably well by a quadratic function near its minimum. Thus, a conjugate direction method is expected to speed up the convergence of even general nonlinear objective functions. So, it follows from the property that we just talked about, that conjugate directions method can minimize a quadratic function in a finite number of steps. Now, any general nonlinear function can be in general approximated well by a quadratic function near its minimum. So, we naturally expect that the conjugate directions method will speed up the convergence even for general nonlinear objective functions. Powell's method first generates a set of n linearly independent search directions. Starting each time from the previous best point, unidirectional searches are performed along each of these search directions. The last search direction replaces the first one in the new iteration, and the process is continued until the function values show no improvement or it meets some convergence criteria, such that the search direction becomes very small or the function value does not show any improvement. Previous search directions are stored in this method and they form a basis for the new search direction. Powell's conjugate direction method guarantees to find the minimum of a quadratic function by one pass of n unidirectional searches along each search direction. For general nonlinear unconstant multivariable functions, more than one pass of n unidirectional searches are necessary. So, if you have a quadratic function in n variables, it is guaranteed that you will be able to find minimum by one pass of n unidirectional searches along each search direction if you are using Powell's conjugate direction method. But for general nonlinear unconstant multivariable functions, that means not quadratic functions, any other general nonlinear unconstant multivariable functions, more than one pass of n unidirectional searches are necessary. So, what is a conjugate direction? Conjugate directions are more effective as such directions than arbitrarily chosen search directions. Two directions S1 and S2 are said to be conjugate with respect to a positive definite matrix Q if S1 transpose Q S2 equal to 0. So, two such directions S1 and S2 are said to be conjugate with respect to a positive definite matrix Q if S1 transpose Q S2 equal to 0. Let Q be an n cross n square positive definite symmetric matrix. A set of n linearly independent such directions is said to be conjugate with respect to matrix Q if Si transpose Q Sj equal to 0 for all I is not equal to j, I equal to 1 to n and j equal to 1 to n. First we said that let us consider two such directions S1 and S2. So, these two such directions S1 and S2 are conjugate with respect to a positive definite matrix Q if S1 transpose Q S2 equal to 0. Now, we can extend this to a set of n linearly independent such directions. So, if I have S1, S2, S3 up to Sn linearly independent such directions, we will say that they are conjugate with respect to matrix Q if Si transpose Q Sj equal to 0 for all I equal to 1 to n, for all j equal to 1 to n and I is not equal to j. That means, you take any two such directions from n linearly independent such directions, any two different such directions from n linearly independent such directions, and then take the product S1 transpose Si transpose Q Sj, check if this is equal to 0 or not. So, all such S1, S2 up to Sn such directions will be conjugate with respect to positive definite matrix Q if Si transpose Q Sj equal to 0 for all I equal to 1 to n, for all j equal to 1 to n and I is not equal to j. For optimization, Q is the Hessian matrix of the objective function. Orthogonal directions are a special case of conjugate directions. In this case, Q is the identity matrix. For a quadratic function of f(x) of n variables, the Hessian matrix H is a constant matrix. For quadratic function, we are guaranteed to reach the minimum of f(x) in n stages if we minimize exactly on each stage. In general, conjugate direction is not a unique direction. In n dimensions, that is for n variable functions, many different sets of conjugate directions exist for a given matrix Q or Hessian matrix H. In 2 dimensions, that is for 2 variable functions, if we choose an initial direction S1 and we choose the positive definite matrix Q, then the other direction S2 is fully specified. This is because the two conjugate directions must satisfy S1 transpose Q S2 equal to 0. So, in case of n dimensional problems, there are many combinations, but in case of 2 dimensions, if I fix S1, then for a given positive definite matrix, S2 becomes automatically fixed, because if S1 and S2 have to be conjugate with respect to positive definite matrix Q, the relationship that must hold is S1 transpose Q S2 equal to 0. So, if we take a numerical problem, it will be clear. Let us say that we want to minimize the objective function 2x1 square plus x2 square plus 6, starting from x0 equal to 1 1, with the initial direction -4 -2. Find a conjugate direction to the initial search direction S0. So, we have been given a function in two variable which is 2x1 square plus x2 square plus 6. We want to minimize this function starting at x0 equal to 1 1. So, that is the starting point, and the initial direction is given as S0 equal to -4 -2. So, you want to find a conjugate direction to the initial search direction S0, that is -4 -2. In other words, the question we ask is find the conjugate direction to -4 -2. So, let us consider that the conjugate direction is S1, which has two components. We have written it as S subscript 1 superscript 1 and S subscript 2 superscript 1. Please note the notation that is used for the two components of the search direction vector S1. It is given that initial search direction S0 equal to -4 -2. Objective function is given as 2x1 square plus x2 square plus 6. So, you can find out the Hessian matrix. So, you find the Hessian matrix by considering del square f del x1 square del square f del x1 del x2 and del x2 square. So, this is your Hessian matrix which can be obtained from this expression, and this is obtained as 4 0 obviously same 0 and 2. Now, to find out the conjugate direction S1, we have to solve S0 transpose H S1 equal to 0, because if S1 and S2 are conjugate with respect to Hessian matrix H, S0 transpose H S1 will be equal to 0. So, put S0 transpose the Hessian matrix H and the search direction S1. So, this has to be 0, this has to be solved. Now, note that this is not unique. In fact, neither is this. So, we can select one and find the other one. So, let us say select this as 1 and then we can find this component. So, if you do that, we write this and then you can find S1 as 1 minus 4. From this you can find out the value of S subscript 2 superscript 1. That means the other component of the search direction S1. So, the search direction is obtained as 1 minus 4. So, this 1 minus 4 is conjugate with minus 4 minus 2 with respect to the Hessian matrix H. Now, we will talk about two properties, parallel subsets property and extended parallel subsets property. Consider a quadratic function of two variables q x equal to a plus b transpose x plus half x transpose q x. Here A is scalar, B is a vector and Q is 2 by 2 matrix. Also consider two arbitrary but distinct points x 1 and x 2 and a direction d. Let y 1 is the solution to the problem minimize q x 1 plus lambda into d, and y 2 be the solution to the problem minimize q x 2 plus lambda d. Then the direction y 2 minus y 1 is conjugate to the original direction d. In other words, y 2 minus y 1 transpose q d will be equal to 0. So, what we understand is, consider this quadratic function of two variables, consider two distinct points x 1 and x 2. If y 1 is solution to this problem minimize q x 1 plus lambda d and y 2 is the solution to the problem minimize q x 2 plus lambda d, then y 2 minus y 1 is conjugate to the original direction d. In other words, it is same as saying y 2 minus y 1 transpose q d equal to 0. Now, this can be represented schematically as shown in the figure. Look at this point x 1 and x 2. So, x 1 and x 2 are the minima of the quadratic function obtained by searching along the direction s from two different starting points x a and x b. So, from x a, if I do an unidirectional search to find the minimum of the quadratic function, I get x 1. Similarly, when I start from x b and perform unidirectional search to minimize the quadratic function, I get x 2. So, this is basically our solution to these two problems. Now, starting from x a and performing unidirectional search along the direction s, I have obtained x 1. Similarly, starting from x b, I have performed unidirectional search to minimize the quadratic function along the direction s and I have obtained x 2. Then the line x 1 minus x 2 will be conjugate to the search direction s. So, the line x 1 minus x 2 is conjugate to the search direction s. Now, let us talk about extended parallel subspace property, which is basically extension of what we have just seen, parallel subspace property. Let us consider y 1 is obtained after unidirectional searches along each of m conjugate directions from a chosen point x 1. M is less or equal to n, where n is the number of variables. So, y 1 is obtained after unidirectional searches along each of m conjugate directions from a chosen point x 1. Similarly, y 2 is obtained after unidirectional searches along each of m conjugate directions starting from another point x 2. Then the direction y 2 minus y 1 is conjugate to all m search directions. Let us just mention this theorem. If a quadratic function q x equal to a plus b transpose x plus half x transpose q x is minimized sequentially once along each direction of a set of n mutually conjugate directions, the minimum of the function will be found at or before the nth step irrespective of the starting point. So, you have a quadratic function q x equal to a plus b transpose x plus half x transpose q x, where a is scalar, b is a vector and q is a matrix. So, if this quadratic function is minimized sequentially once along each direction of a set of n mutually conjugate directions, the minimum of the function will be found at or before the nth step irrespective of the starting point. So, now let us present the algorithm for Powell's conjugate direction method. So, in the step 1, we define the starting point x 0. We also define a set of linearly independent directions. In the step 2, we minimize along n unidirectional search directions using the previous minimum point to begin the next search. Start the search with S 1 and end with S n. So, you have n linearly independent search directions S 1, S 2, S 3, S 4 up to S n. So, you start the search with S 1 and end with S n, then perform another unidirectional search along S 1. Now, use extended parallel subspace property to form new conjugate direction. Let us say this new conjugate direction is D. Now, if the norm of D is small, that means magnitude of D is small, or search directions are linearly dependent, we stop. Otherwise, we replace S j as S j minus 1 for all j equal to n minus 1 up to 2. Then we normalize the search direction as we set S 1 equal to D divided by norm of D and go to step 2, where again we minimize along n unidirectional search directions using the previous minimum point to begin the next search. So, this is how the algorithm goes. What you do is you define the starting point first, define the set of linearly independent directions S 1, S 2 up to S n. You minimize along n search directions using the previous minimum point to begin the next search. You start the search with S 1 and end with S n, then you perform another unidirectional search along S 1. You use the extended parallel subspace property to form new conjugate direction D. If the magnitude of D is small or such directions are linearly dependent, we stop. Otherwise, we replace the old search directions. So, we replace S j equal to S j minus 1 for all j equal to n minus 1 up to 2. Normalize S 1 as S 1 equal to D by norm of D and then again go to step 2. So, now let us consider an example. We want to find the minimum of a 2 variable function, which is given as 2 x 1 cube plus 4 x 1 x 2 cube minus 10 x 1 x 2 plus x 2 square. The starting point is 5, 2. So, to start with, I have to define the search directions. How many search directions? 2 search directions, S1 and S2. So, we can consider the coordinate directions. So, we can take S1 as 1 0 and S2 as 0 1. Note the function value at x 0 is 314 if you calculate. Now, we have these 2 such directions, 2 linearly independent search directions S1 and S2 as 1 0 and 0 1 respectively. In the step 2, you have to find x 1, x 0 is given, you will find x 1. So, what we will do is we first find lambda. So, find lambda such that f x 0 plus lambda s 2 is minimum. So, basically you are performing unidirectional search along S to minimize the function. So, find the value of lambda. So, how will you do that? You can make use of the unidirectional searches that you have learned. You can also do as follows: f x 0 is what is given as 5 2 plus lambda S 2 is 0 1. This is f of 5 2 plus lambda. So, you put x 1 equal to 5 and x 2 equal to 2 plus lambda in the original expressions. So, we will get an expression in terms of lambda. So, you will get a function of lambda. Then you can set df d lambda equal to 0 and find the value of lambda. So, let us consider that lambda is lambda star or lambda 1 star. So, I get lambda 1 star from here. So, lambda 1 star I get while I minimize along the search direction S 2. Remember, my S 1 was 1 0 and S 2 was 0 1. So, once I have got the lambda 1 star, I can find out x 1. How? I can find out x 1 as x 0 plus lambda 1 star S 2. So, this can be obtained as x 0 was given as 5 2 we have obtained lambda 1 star and S 2 is given as 0 1. So, this will give you the value of x 1. You put the numerical value of lambda 1 square, lambda 1 star as you have found out optimally in the previous step. So, you get the value of x 1. Now, once I have the value x 1, I will now perform a search direction along S 1. So, I do the same thing. So, I find lambda, in fact, I find now I will call say lambda 2 star such that f of x 1 plus lambda 2 star S 1 is minimum. So, again you can make use of unidirectional search techniques that you have learned, or you can express the expression in terms of lambda 2 star and can find out the value of lambda 2 star by taking the derivative df d lambda equal to 0 and can obtain the value of lambda 2 star. So, once you have the value of the lambda 2 star, you can get x 2 as x 1 plus lambda 2 star S 1. So, x 2 is now obtained. Once x 2 is obtained, I will perform another unidirectional search along S 2. So, again I ask the same question, find lambda 3 star such that f of x 2 plus lambda 3 star S 2 is minimum. Once you have obtained the lambda 3 star value, you can obtain x 3 as x 2 plus lambda 3 star S 2. So, this will give you the value of x 3. We have obtained f of x 0 as 314, then you will obtain the value of f of x 1, f of x 2, f of x 3. Now, I was given x 0, I got x 1, I got x 2, I got x 3. We obtain, look at the values of f of x 1, f of x 2, f of x 3. I will now obtain the search direction x 3 as x 3 minus x 1. Then you can normalize S 3 as S 3. You can put it like this as well. No. So, now set S of 1 equal to S of 2, S 2 as S 3, and then go to the step where again you perform unidirectional search along S2, then along S1, then again along S2. So, this is how you will continue. If the function is quadratic, you will see that you will obtain the solution after this round. With this, we stop our discussion on Powell's conjugate direction method.